And bonjour. This is the Darko and Bruno excellent podcast where we talk about biostatistics and AI. And sometimes we go back in the past and the history of some of these technologies and techniques. Today, we're going to talk about network meta-analysis with Darko. I'm here, though, in San Antonio for the San Antonio Breast Cancer Symposium, which is started yesterday. And there's going to be a lot of data. I'm sure there's going to be some NMA, some network meta-analysis. So if you are interested in NMA, if you already are an expert in NMA and you want to find mistakes in what we're going to say, or maybe new ideas as well, by the way, because we have some new crazy ideas to share with you. If you want to know who invented NMA, this is a podcast for you. Darko, welcome to the podcast.
Thank you so much, Bruno. Always amazing to be here. And yes, today we're going back to the past, talking about who invented network meta-analysis. And we like doing that. We like going back to the past and studying how it all started.
And by the way, Darko is a very experienced statistician. I'm not. So I'm the naive guy here who can ask some silly questions, but he's the one who knows what he's talking about. I would just add that LARVOL is a cancer data and AI company, and we develop products at the intersection of cancer data, AI, and biostatistics. We actually have in our data studio online a NMA tool that Darko helps us build. So maybe at the end of the podcast, we'll give an idea of what's next in the NMA world. So back to you, Darko, about the history and the timeline for the development of NMA.
Yes, so back to the history. NMA is actually, and that's very interesting, you could call it a modern discipline. You know, on some of the previous episodes, we were going centuries in the past to discuss who invented the frequentist and the Bayesian framework and everything. But when we talk about network meta-analysis, it was actually formulated not so long ago, a bit more than 2 decades from this moment in the past. So the roots really start in maybe 25 years ago, when a number of scientists, biostatistician scientists, were actually thinking how to do indirect comparisons. So if you don't have a direct comparison in a study or in a clinical trial, there were ideas in maybe 1995, 1997 about how to conduct those. And one of the names we can mention is Hans Bucher.
How do you spell that? Oh, you don't. That was actually a year of Fight Club, right? When did Fight Club come? Was it 97, maybe 98?
Yes. It's something like that, you know. So actually, it coincides. It's a very interesting coincidence. Yes.
We don't talk about Fight Club, but we talk about NMA.
Yes, that's interesting, you know. And we had the Brad Pitt, and in Fight Club that year, and a lot of interesting actors there. But
now, clearly, the Brad Pitt side is a Bayesian, by the way, and the Ed, what's his name, is a frequentist. No?
Edward Norton. Yeah, Edward Norton. Actually,
he's a frequentist guy in that pair. No.
Yeah, so I'm quite sure that's the case. You know, Brad Pitt is probably a Bayesian. So, you know, it's difficult to have arguments, with Brad Pitt. But then we also have the Edward Norton. You know, I'm a really big fan of Edward Norton, and I'm a frequentist. Just probably the Edward is as well. So going back to the same year, Hans Bucher actually created a statistical method where, you know, even if you don't have a specific direct comparison, but you can somehow indirectly infer it. So, for example, if you have a comparison A versus B, and you have a comparison B versus C, but you don't have a comparison A versus C. You can infer it from two other comparisons, right? So that was really one of the first baby steps of network meta-analysis, which later turned into a large-scale framework of NMA, which was formulated maybe several years later, I think in 2002, by Thomas Lumley, another fantastic statistician who actually created the network. And he said, well, we can do this in indirect comparisons. We can have more treatments at once, and they're all connected to each other in a network. And that's really where the whole story starts and develops into what we have today.
So walk me now through the steps. Let's say I want to do an NMA. What do I need? What are the steps? And what is the outcome of my NMA, of my network meta-analysis?
Well, the outcome is very interesting. So NMA is often called multiple treatment comparison, or MTC, right? So we have usually multiple treatments. It could be multiple versions of the same treatment, like multiple doses of the same treatment, but usually it's multiple treatments. And that's a novelty compared to most other meta-analyses, which are pairwise. Like you have intervention and control, and then we just repeat that intervention, control, and then we combine all those together to get the meta-analysis result. However, in NMA, we have multiple treatments, which we use to form the network. And so that's the first obvious output, is that you can compare those multiple treatments. And majority of people think that's the core of NMA. However, the core of NMA and the biggest advantage is that we can get this indirect evidence. So if we have, let's say, 20 treatments, and only for some of them direct comparisons were conducted in RCTs or other studies, I don't know, other experimental designs, but there are a lot of gaps in the knowledge. A lot of studies are unfeasible. For some reason, they were not conducted. NMA allows us to infer indirectly what would happen if we conducted those trials that don't exist in the network, that were not really conducted, but we can use all other evidence from the network to infer them. So that's the biggest advantage. You can take a study, hypothetical study that was not conducted. If you have enough evidence which indirectly can infer the results, we could estimate quite accurately what would the treatment effect of that hypothetical study potentially be. I think that's the biggest advantage.
And I guess that's useful because in many cases, there's not going to be any head-to-head comparison, right? The incentives are just not there, mostly for pharmaceutical companies to do head-to-head. So when they're approved, they don't want to do head-to-head. Maybe they're afraid that they're not going to win. So no face-off, very rare, right? That people do face-off. They always compare to standard of care, to the previous standard of care, to chemo, to placebo, sometimes rarely. So no direct comparison. So we do indirect comparison, NMA. That's the idea. And now we need to pick which study are going to be in the NMA. How do we pick the study that are going to be included in an NMA?
Yeah, so NMA is, it can be complicated, and there are assumptions that need to be true in order for NMA to work. So one of those assumptions is transitivity. And transitivity pretty much revolves around the fact that the designs that we are including and the population that you and I often discussed, the key population that is in question, they must be similar enough so that we can assume that if we have this transitive effect, this indirect transitive effects, that similarity is high enough so that we can safely assume that, if I compare A versus B and B versus C, well, then I can also infer something else. I can infer A versus C, which was not directly uh, not directly part of the comparison. There are other assumptions, but essentially it's a lot about having study designs which are similar enough, and especially the controls that are used in those study designs. Controls are very important.
Okay, so you pick comparable trials that should be compared, and then you can derive indirect relationship between the different regimen, so different treatment of these trials. And then the output is a ranking with a spatial score for each in terms of how well it works, right? A stack. Is that correct?
Yes, that's correct. That's really the end result that we would get. We can use both direct and indirect evidence and then combine them together to get, how would I say, a more powerful version of evidence base, and then use that evidence to create a ranking score. So we can rank treatments, like this treatment is the best treatment effect, and the second, the third, the fourth. We can rank them according to the strength of evidence that they are better
Yes.
or worse treatment effect. And this score is called the p-score in frequentist framework. And for our listeners, it's important to not confuse that with the p-value, right? So the p-score is, yeah.
I was confused.
Yeah, so us frequentists, we like to use term p, like p-value, p-score. We use that term a lot, and
the Bayesian don't like that too much, right?
No, the Bayesians, they don't like the p letter at all. They actually have their own version of p-score, which is called Sukra. So Sukra, yes, this Sukra value tells us how to rank, like what is the best, what is the second best, and so on.
And Sukra stands for something, or it just means sugar, and you add sugar, and
yeah, it actually reminds us of sugar, but it's actually, it's actually this network derived, often from indirect and direct evidence combined, network derived evidence that will tell us, like, yes, when we combine all that evidence together, it points us that this treatment should be on top. Now, the Bayesians would say, no, the Sukra is the main thing, but the p-score is just an alternative, So,
yes,
depending who you ask, they will tell you, no, it's the main thing is what we do, and the other side is just copying us.
Yes. So in previous episode, we had a little bit of a fight between the frequentist and the Bayesian. So okay, and so what's next in the field of NMA? Right? I mean, it's a new field, and synthetic evidence. Is it okay to call it the synthetic evidence? Meta-analysis, pool analysis, pairwise meta-analysis. Is that what it is?
Yeah, I think that's a very fair statement. And what most people don't know actually is related to this, that network meta-analysis is one of the most reliable approaches to create synthetic data for clinical trials. So the same principle that we were discussing before, where we do not have direct comparison, we do not have a study that corroborates some evidence, but we can infer it, effectively creating synthetic data for a hypothetical synthetic trial that would occur between two or more treatments. So that's really interesting, and that's of course that's something that we are also working on with LARVOL, and we have our own NMA module that is now being combined with special advanced approaches, which we'll probably be discussing on some other occasion.
So,
but yeah.
So I know we're close in time, but imagine. So I'm the non-scientist, so I can imagine anything I want. Imagine the NMA of every cancer drug and treatment. Okay, and so it's like a knowledge graph with nodes and and edges, and it connects every single regimen treatment from every single trial in a big knowledge graph powered by AI. Could that work in the age of AI? Could we
I
make derive indirect synthetic evidence from such a graph?
I think it could. It's definitely a novel approach. So we'd probably be one of the first to try, but I think it actually could, because if you look at what's happening with the world of AI, at least the angle about biostatistics, you will see that large language models are not very effective at doing
Right.
biostatistics, and
Yes.
one of the main problems is a lack of reproducibility and reliability. And with NMA, we actually get that angle. So this combination could be very special, where we have the power of AI, but we also have reproducibility and reliability of an approach like NMA. And of course, that applied to a large scale, as you suggested, like all the oncology trials that we can combine. That would be a very unique approach, I would
Yes.
say.
Well, we're going to invent new methods here. Hey, Darko, thank you very much for joining. End of podcast, and we'll see you next week for another episode of Darko and Bruno, biostatistical and AI, etc. All right. Au
Au
revoir.
revoir. By the way, Bruno, until the next one, we actually have to invent the new NMA method. I
Oh
think we should
yes,
do that.
we do. We have to,
Yeah.
we're still on, but that's okay. I think
Oh,
let's not say anything bad about anybody. Or maybe we
yes.
do. We'll have a cover. We didn't know.
Oh,
We
just
can.
good things. Just good things. Okay.
We say
Yeah.
good things about frequentists
Yeah.
and about Bayesian. Well, we should say the good things about Bayesian too, because
We
Bayesians have
have to.
people too. We have to. They need more love. That's the point. They didn't get enough love when they were
So
little.
yeah.
That's why they're cranky, and maybe they're right, but nobody wants to party with them. Nobody wants to date them. They cannot get a drug approved through the FDA. No wonder they're cranky, right?
Hey, I mean,
So
what can I say? No, nobody wants to party with me either. So
that's why that's when you were a Bayesian, right? Now you understood. No, no,
yeah. I was
I
actually a
have to.
Bayesian, so I have to send love to the Bayesians, because I was a Bayesian once, and there is still like a Bayesian inside me, maybe
There is always a
waiting,
Bayesian inside us. There's
waiting.
always a
Yeah,
Bayesian without us. To me, it's the difference between, do you want to be right or do you want to be successful? If you want to be right, you probably want to be Bayesian. They're probably right. But if you want to be successful and get a drug approved or just be published, man, I don't know. Or
I mean,
make a presentation at ASCO. You need probably to be a frequentist. I'm sure our Bayesian friends, and we ought to
yeah,
have one or two Bayesian friends. We should. They need all the help they can get. Would disagree with that statement. So
yeah.
our executive producer Shahir Sheikh, who normally ends the podcast, kept us going, maybe on purpose, to see if we would say anything incriminating.
Yeah.
Oh,
Shakir is.
maybe she just got disconnected.
Yeah, maybe.
Enough
Anyway,
with these guys.
Thank you,
I think.
everyone. Who tuned in. This is Shahir from the background. Thank you, Bruno. Just wanted to
Oh, he's
chip
back.
in and say hello. There's quite a few people connected, so I just wanted to acknowledge that, and thank you everybody for keep tuning in for these live episodes. Thank you, Bruno. Thank you, Darko. Anything as we end?
No, I
Again,
just want to say,
yes.
we figured that Brad Pitt is Bayesian, probably. So that's a big argument for the Bayesians. Yeah.
So I will be I think he had a very short haircut during the Fight Club. So you'll be Edward Norton. I'll be your alter ego,
Yeah.
Brad Pitt.
We should make a Fight Club edition, definitely.
Eh. All right. Au revoir.
Au revoir.